Good evening or afternoon. How is everybody doing?
Okay, thus far, sir.
Good. Okay. Wonderful. All right. Again, I had a couple of videos up. I'm gonna make a final. I'm pushing. First of all, let's do a little housekeeping stuff. I'm pushing for with your program director to see if we can get something concretized as it relates to the assessment for this module. I haven't gotten it as yet from him. For me, I made certain suggestion. He said that he'll give me a feedback sometime tomorrow. So as soon as I hear something, I'll send a post that info to you. Okay, Chad?
Yes, sir, no problem.
In the interim, whatever happens, based on what we would have done with the Z transform, and what we'll be doing or what you'd have been watching, I'm going to be giving you guys an assignment during this week, a 1 week assignment, okay? As our first assessment. And as I say, as things unfold, what we'll do is wait. I'll be guided based on further instructions. All right. For me, again, I want you guys to tell me from watching the videos, what it is that we would have garnered. What are the key takeaway that you would? So the first one is looking at the basic concept, because I'm going back based on what you told me. Again, I have no knowledge of whether or not it is or isn't the case, but I take your guys' word for it. That pretty much you, with what you would have learned without Mr. McLeavy's input. So I start looking at DTFT, which is really the concept of going from continuous signal to discrete signal, how the process is evaluated, and how information can be represented. And I have two videos up there. One is just a 5-minute video, and I think the other one is just about 1 hour. Have you guys got a chance to look at these videos as yet? And if so, what are the main takeaway that you guys would have gotten from these?
I'm sorry, the 5-minute one was the overview one, right?
The overview, yes.
Well, yeah, you had already heard last time what I took away from it in terms of I'd have to watch it again. Since it's been a while, I'll have to watch it on the hour one again. But you heard my main takeaways in terms of, and you showed us the last time as well, in terms of the what do you call it? Wow. I forgot to watch it again, sorry.
All right, fair enough. Anybody else?
Well, if I could add something to that, some of the issues, well, not really a takeaway, but some of the issues that I have was like trying to, I'm not sure if it was identities that they were using. I don't know if you want to call them identities, but like certain proofs that were being done to prove the different types with doing some of the calculations in about 1 hour in, about 50 minutes into the video. I wasn't getting most of them so clearly to understand exactly how it came up with the equations and some of the assumptions being made. I'm wondering if it's maybe something you had made a such a statement to say that we should, you're not trying to teach us back signals. I'm wondering if it's from that area where I'm actually, that's making it a little bit more challenging for me to understand.
Okay, so Vernon, I hear you. The question I'd ask you though is what have you done in terms of
Trying to.
in terms of freshening up, in terms of revisiting. What have you done? Anything that you would have seen that you would have? Because nothing here is really new. So what? Anything that you would have done, and you don't necessarily have to answer it right here and right now. This is a self assessment. And you can answer that question. But I'd like to hear from someone else in regards to what their main takeaway from watching these videos in terms of understanding DTFT and the concept of moving from CT continuous time signal to discrete time signal. All right. Again, gentle people, as I say, it's kind of hard when we don't, and you would have had a lot of time. What I hear you, Sir Richard, and what I'd love is for a specific thing that you'd want to point out in your challenge, and I appreciate if others, listening to you, could have shared what they would have learned. And I'm 100% sure whether or not persons have watched. We're gonna do this. I'm gonna go through the 5-minute one, which is really an intro to the concept. I'm gonna put it that you guys watch it. So you see my screen?
Yes, sir.
All right. So I'm gonna play it. I'm gonna mute my mic just in order for you not to get any feedback. All right. You can make your comment. I will stop and pause it accordingly. Okay.
Yes, sir. Got that.
Here we go.
In the digital control part of this module, we have looked at modeling discrete time signals and systems. We will use these concepts in the rest of the module to model systems that contain both discrete time and continuous time components. However, before we move on to such it would be insightful to pause a bit, look back at all the techniques we used for modeling discrete time signals and systems, and contrast it to the more familiar techniques for modeling continuous time signals and systems. The topic of this video is therefore an overview of discrete time modeling techniques and a comparison with continuous time modeling techniques. The signals we consider are discrete time signals, which are only defined at integer values of the time index k. We contrast them to continuous time signals, which are defined for any real value of the time variable t.
Just that by itself, is everybody clear as to what has just been said?
Yes, sir.
Yes, sir.
And this system. Okay, on Richard.
We're talking about the real time, like seconds, signals that, like, for example, I'm guessing probably like a sine wave or something of that sort. That kind of a signal, analog signals.
Yeah, so what happened on the left-hand side, you have the continuous time. So you see the variable of t, while the discrete time, what you're looking at is a variable of a period of time. Because remember now, what's going to happen is that discrete signal is going to be up for a period of time. And the period of time is defined by k. Now, a continuous time, if you're looking at the signal in terms of continuous analysis of the signal continuous time, you're looking at basically at an instant in time. But for k, k time could be over a period, going from 0 to, x or infinity, as I would say. Because what happened is that the discrete portion of the signal, remember digital signal, it moves from one voltage level to our next voltage level, and it stays there for a period of time, right? And that's the time we're talking about as compared to an instant in time where the continuous signal is basically analyzed at that instant in time t. All right, let's go again.
The systems we consider are linear time-invariant discrete time systems, here depicted with input signal R of k and output signal Y of k. We contrast them to linear time-invariant continuous time systems, here depicted with input signal U of t and output signal Y of t. One way to model discrete time systems in the time domain is with difference equations, where we describe the relationship between a system's signals and their time-delayed versions. The analogous continuous time model is differential equations, where we describe the relationship between a system's signal and their derivatives. Another way to model discrete time systems in the time domain is with the impulse response, which is the output of a system in response to a discrete time impulse input signal. The analogous continuous time model is the continuous time impulse response, which is the output of a system in response to a continuous time impulse input signal. We also model discrete time signals and systems in the Z domain. This is useful to do since certain operations are easier to do in the Z domain than in the time domain, and the dynamics of a system can compactly be described in terms of Z domain properties. The analogous continuous time model is the Laplace domain. We convert discrete time signals to the Z domain by applying the Z transform, and the resulting signal is described in terms of the complex variable Z. A signal in the Z domain can be transformed back to the time domain by applying the inverse Z transform. A continuous time signal can analogously be transformed to the Laplace domain by applying the Laplace transform. The resulting signal is described in terms of the complex variable S and can be transformed back to the time domain using the inverse Laplace transform. Discrete time systems are described in the Z domain as transfer functions. The transfer function is defined in two equivalent ways. It is the Z transform of the impulse response of the system, and it is also the Z transform of an output signal divided by the Z transform of the corresponding input signal. Continuous time systems are described in the Laplace domain by transfer functions, which are analogously defined as the Laplace transform of the impulse response of the system and the Laplace transform of an output signal divided by the Laplace transform of the corresponding input signal. We draw block diagrams of discrete time systems using gain, summation, and unit delay blocks. One can therefore think of the unit delay block as the basic dynamic unit of discrete time systems. The transfer function of a unit delay is 1 over z. Analogously, we draw block diagrams of continuous time systems using gain, summation, and integrator blocks. The basic dynamic unit is therefore the integrator, or 1 over s. It is important to note that this does not mean that the unit delay can be thought of as a discrete time integrator. The discrete time integrator has a different transfer function. We concisely describe the dynamics of a discrete time system by calculating its poles and zeros from its transfer function. We often plot these poles and zeros on the complex z-plane. For a continuous time system, we calculate its poles and zeros in the same way from its transfer function, and we often plot them on the complex s-plane. However, the location of poles and zeros on the s-plane cannot be interpreted in the same way as poles and zeros on the z-plane. We have already seen that poles within the unit circle in the z-plane are stable, whereas stable poles are located in the left half-plane of the s-plane. We will look at ways to map discrete time poles from the z-plane to equivalent locations in the s-plane at a later stage. Doing this will allow us to attach more meaning to pole locations in the z-plane. In conclusion, we can see that there are several similarities between modeling discrete time and continuous time signals and systems. We can exploit this fact to improve our understanding of discrete time signals and systems. However, there are a few significant differences, and one should be careful not to assume similarities when there are none.
Okay. All right. Any questions? Clarification needed?
Yes. Sorry.
Mm-hmm.
So what is being said, just for clarification, is that the continuous time and the discrete time, they are different in the sense one is analog, one is digital, correct?
That's correct.
So we are doing, because for some reason I remember seeing the continuous time being converted to discrete using a particular method. I think it's the is that a thing? I'm sure I've seen it. CFT to DT or something of that sort. Converting from the continuous to a discrete time, right?
You can convert from continuous to discrete time. Remember now, what happens is if you have an analog signal, continuous signal, that
Yes,
signal can be digitized, right?
Yes, sir, through sampling.
The thing is, and I try to explain this at the onset of in terms of our class. One thing you need to understand is that what you're doing is looking at, you're putting in a signal, the input of a system, and that signal is being outputted. And that system is a black box, which is going to do something to the input signal when seen at the output. How you analyze that is different, because if you just look at just converting analog signal to a digital signal, it's going to be different, because what happened is that the discrete analysis of signal performs a more complicated a transformation of the signal, but a more realistic conversion of the signal as it transfer from input to the output. With the analog system, when you're doing the conversion, what you're doing is that you're going to be doing a lot of estimations, for argument's sake, including rounding up and rounding down and so on. One other thing that you need to understand is that the signal, when it comes to the continuous transformation from input to output, you are, again, there's a thing that is called quantization error and quantization losses that will be significant. And therefore, some of the information cannot be readily be represented in terms of the analog. And that's why they say the Laplace transform of a system is not a total representation of the complete signal as a transfer from input to output. A better representation to include complex numbers is using the Z transform or using the DTFT system, which what it does is give you give a representation of whether or not the system is stable So remember, I don't know if you remember we talk about the system being conversion, if it's system converge or not, right?
Yes, sir. With
Right.
the unity circle.
So the continuous time representation will not provide that information. It will give you poles in the left hand side of the graph, the complex representation, a complex number representation, but doesn't necessarily tell you whether or not the system is actually conversion, which is really tell you whether or not the system is steady state, that we'll talk about you getting the same thing each time you put the thing in. So it's not one time you put the thing in, but because of the poles and zeros, you find that the system is overshooting or underdamping. Or in other words, a basic thing is that it's not performing the same time, the same way based on what you're expecting. And that's why it's a little bit better to represent the information. But we can find ways of moving, which is what the gentleman had said at the end of it, from representing information from the DTFT to the CT format, and then you can have a look and a comparison to see how it is represented, which is what to some extent is shown in the second video. All right, any other question? All right. Any other question before we move on to the next?
No, sir.
Sir. Can you hear me?
Yeah, man, I'm hearing you. Just remember that I put my, in order to watch the video, I have to mute my thing as to get a feedback. So when you ask, I have to go back to unmuting. Yes, I'm hearing you now.
Oh, okay, sir. Is it possible to have some questions done as it relates to the, because you might watch a video, get information.
You're breaking up, but if you're asking about getting questions, and remember how we looked at the Z transform and I gave you questions as well. Remember, I post questions there, how to work them. Is that right? I don't know if it's me who is gone or Mr. Wright who was gone. But it's the same thing. So we're going to try to understand the basic concepts, and then we look at how, if given questions in a particular format, how it is that we approach it based on our understanding of what was done. So if you're hearing me, Mr. Wright, that's the approach, okay?
We're still hearing you, sir. It's probably just his internet.
Okay. All right, so we're going to go to the next video now, all right? So I'm going to mute my mic again.
We've been staying so far in continuous time, right? And so now we want to get to some stuff that you probably haven't seen in a previous class, which is the discrete time Fourier transform. So from now on, we're really mostly interested in signals that are, discrete time, not continuous. So let's remember, the continuous time Fourier transform. Which sometimes they may abbreviate like CTFT, just to be super clear. So we talked about that in the previous couple lectures as being this integral. And this was when I had a continuous time signal x of t, right? But what I want to know now is how can I deal with a signal that is not continuous, but instead is represented like these kinds of, sticks at different heights, what we call X of n. Okay, where we assume that these sticks are indexed by integers. So, our intuition is that what I want to do is I want to turn the integral into a sum, right? So instead of integrating over all the continuous values of x and t, over all the discrete values. And in fact, that is true. So we can define the discrete time Fourier transform, or DTFT, as, I should have given myself a little more space here. Yeah, okay, that's good. It's still a function of frequency, omega. And instead of an integral, I have an infinite sum. Okay, so there's no more dt because I've got a discrete time sum. Okay.
Yes, sir.
The fact that we're in the discrete time, right? How is it that we're in discrete time? How is it that we still speak of the we're using omega just the same? Or is it continuous? So I'm getting a bit confused there.
Okay. All right. Remember now. Okay. Just going back to the representation of the signal, right? What happened is that you have the same signal, which was a continuous signal, going up and down the horizontal line, right? Which t is not been broken. Remember now, t not been broken. Sorry, doesn't necessarily mean that the signal is not periodic, meaning it's not represented. It's not it is still a representation. So let's go back to the let me show you what I'm talking about. What I'm on it. Hopefully I'm not. Good. Are you seeing it? Are you seeing my screen?
I'm still just seeing the YouTube video, sir.
Right, that's what I'm saying.
Okay.
So look at what's happening now. Are you seeing my marker moving?
Yes, sir.
Okay. So here it is a continuous signal that is moving. Okay? Here it is that you have the same continuous signal being represented here. But what you're doing is that you're taking times of representing the continuous signal. But instead of taking it in terms of time, well, you're taking it in terms of integers, particular values, n. See?
Okay, so it's just...
I'm taking this. So it doesn't mean that the signal is still not periodic. You understand me?
Okay, I see.
Okay. All right. So
it's just the way how it is represented. That's what makes it discrete.
Yep.
Okay.
Remember, I go back to basic, and again, for those who did digital with me, as in digital electronics, the key thing that you need to remember is how do we define a analog signal as compared to a digital signal or a discrete signal? And the definition is simple. The analog signal, the amplitude of the signal is changing at every interval of time. So it's changing with time. Okay? A discrete signal or digital signal, the amplitude is not changing with time as time continues. It changes. So every instant there is a value. So every instant of time there is a particular value. It's not changing. So the amplitude is not changing with time. At an instant in time you get an amplitude. That's it. Follow me?
Yes, sir, got that.
Okay.
You did say this before, but I'm not sure. The discrete, I guess, is what is throwing me.
Discrete Okay, so what's a discrete signal?
Well, basically, from my understanding, it would be a digital one that is digital that doesn't change.
Okay, so right, so discrete just simply means is either the signal is there or it's not.
Not right.
Okay.
Okay, so I'll continue to bear that in mind going forward.
All right.
Thanks for that, sir.
No problem. So I'm gonna mute again. I will continue playing.
So this is still a continuous function of omega, right? So I haven't, made the frequency domain discrete. Right now, that's still continuous also, okay? And so, like I alluded to on the first couple of days of class, there is.
So you see, that was clearly just stated, right?
Yes, sir.
There's a difference, though, right? Because here, for the continuous time Fourier transform, we can have frequencies that are arbitrarily high, right? We can make cosines that are arbitrarily wicked. And so I could have a cosine 5,000 hertz, a cosine of 10,000 hertz, a cosine of 100,000 hertz, right? That's not a problem for continuous time. But in discrete time, it turns out that we only have a fixed set of frequencies. So why is that? So what I was saying earlier just now is continuous time Fourier transforms have a frequency range that is basically unlimited. But discrete time Fourier transforms have a frequency range of width 2 pi. And why is that? Well, if I take my definition and I plug in 2 pi plus some arbitrary omega, what I have is this sum, e to the minus j omega, and I guess I should say omega plus 2 pi times n. And so I can pull out this guy here, e to the minus j omega n, and then I have this e to the minus j 2 pi n, right? And the thing to remember here is that n is an integer. And I think about where that complex number is on the unit circle, and it's always right here, right? So this is like 0, then I go around once, that's 2 pi, I go around twice, that's 4 pi, and so on. So no matter what n is, this number always reduces to 1, and this here is just x omega. And so perhaps it would be more accurate to say that the DTFT can be evaluated for any omega, but it's 2 pi and periodic. Okay, so if I were to think about the DTFT, what it would look like would generally be something that looks like this, where I have repeated copies of whatever is happening in the middle every 2 pi units, right? So what happens in practice is that we usually restrict our attention to this range between minus pi and pi, and only draw the DTFT inside this 2 pi wide interval, with the understanding that the DTFT actually has copies out at other omegas. Okay. And again, one of the reasons why we choose minus pi and pi as the boundaries is that if I think about what is, e to the j pi n, right? That's cosine pi n plus j sine pi n, right? And again, I think about where that complex number is, right? So when n is 0, I'm over here. When n is 1, I'm over here. When n is 2, I'm over here. So basically I'm between plus or minus 1, right? So this is basically going to be plus or minus 1. Or a more accurate way to say it would be something like minus 1 to the n power, right? And if I draw that signal, it looks like something that alternates between plus and minus 1, as fast as it can go. And so in some sense, this is the highest frequency discrete time signal that I can create, right? So it kind of stands to reason that I draw my boundary edges at plus or minus pi. As we're going to talk about in just a second, there are some symmetries that when everything is real, I often just draw from 0 to pi because I know that I can predict what the left-hand side looks like given the right-hand side. Okay. So any questions about that? So let's talk about how to go back.
And I too ask a question. Is there any question so far?
Well, sir, I guess I see how it goes between 0 and 1, but I'm not still trying to piece together, like from the top diagram, or top graph, I should say, how does it oscillate like that just from that period or that graph? How does it translate to be like that? Or is it a case that it is representing the entire
Are we okay? Are we looking at? Are we talking about this particular screen right now? Are you talking about that?
Yes, sir. The discrete graph that is being displayed to the lower, the base of the screen.
How do we get this?
Yes, sir. From the top one.
From this?
Yes, sir.
Okay. All right. So e to the j omega t is a complex number, which is always represented. You know, e to the j is cos j cos the real part of a number plus j sine, which is the imaginary part of the number. You know that, right? Because remember that j
Yes,
is
sir.
good. All right. So if we have this as a case, all right, it means that the only thing that will change in this equation is n, where n changes to, so you have n pi, 1 pi, 2 pi, 3 pi, 4 pi, because n is a number, 1, 2, 3, 4, 5, 6, 7. Agree?
Correct, sir.
Okay. So, sorry. If that's the case, if that's the case, we know that as a complex number, but I know it should from the Z transform. Z transform is going to give you a representation of a unit circle, right? Where you can have conversions or region of conversions either inside or outside of this unit circle, right? But the values are usually represented on the complex number is a number that is represented somewhere on the unit circle. You understand that?
Yes, sir.
Okay. So if that's the case, it means that when n is 1, what do we have? What's the cost of pi?
-1.
-1. Okay. And this portion is going to give you what?
0.
Okay. What about when n is 2?
You'll get a positive 1.
Okay. So you see why it's fluctuating between this point and this point now?
Yes, sir. Yes, sir. Yes, sir. I got that portion, but how does it?
Okay, fine. Okay. So we're saying that n is what? N is a
Integer.
n is an integer, which is 1. What is n representing?
I'm guessing the amount of, what would I say?
Anybody else? What is n representing? Here.
So would it be the period or something?
And representing a time.
The time of the
Time when you, the time,
discrete time.
yeah. Remember also that at each interval of time, you're going to take a sample. The sample is going to always be a value somewhere in the unit circle here because a complex number as we realize, eh? So these are the different intervals of time. N, so either n equals to -1, -2, n equals to 0, n equals to 1, 2, 3, 4, 5, 6. These are different what? Units of time, right? Different time. So
Yes.
what we're doing is that we put in values for n, which is now going to give us the value based on what pi or n is, because it's going to be n pi, and it depends on what pi is. Sorry, depending on what n is, we're going to be either up here or down here. What makes that happen is because of fact that as you mentioned before, a cos of 0 is, and cos of 1 is, because remember, a cos of pi. So if this is 1, it's 1 pi. Cos of pi, minus 180. If n is 2, then we're going to have 2 times pi. 2 pi is what, a 360? So that means we're going to be back over here. So we're going to go all the way 360. So we're going to be back over here. Yeah?
It's just multiples of pi in this
Exactly.
instance.
So we're going to have in different intervals are integers of time, right? So you realize that for different values of n, we're going to get, and you know why we get -1 here, right?
I know the reason why it's there.
What's the reason why it's here?
Well, it represents we did it in math. Can't remember exactly, but I know that it's equivalent to that the cosine pi.
There's nothing in maths that is going to make it up there. You can see right here. When n equals to 0. Yeah?
Yes, sir. That number
When n
always
equals 0,
equals 1.
we're going to have what? 0 times 0 times pi. What's the cost of 0? Yes, Juno. Right there. Hold on. The cost of 0 is what?
1, sir.
Okay.
So
All
you
right.
here now?
Yeah, man, I'm hearing you guys.
Yes,
So
sir.
I'm
1.
saying, right. So I'm saying, go back to this. Oops, where am I? Oops. Yeah. So go back to this. Right? So cos of 0. That's when n equal to 0. The cos of 0 is what? 1. So realize that at 0, you have a 1. When n is 1, so when n is 1, we're going to go down here. When n is 2, we're going to go here. So we're going to get the value of plus or minus 1, and that value is going to depend on n, whatever n is. Okay? When n is 2, for argument's sake, minus 1 square is what?
1, sir.
Okay? So you see, when n is 2, we're going back positive, which is really telling you it's really the cos of 360 degree.
Mm-hmm.
And n doesn't necessarily have to be a positive integer, because it could be a negative value as well. That is why we see, you notice if you look at here, we see that we have right up here have minus pi, minus 2 pi, minus 3 pi, but it's going to be multiple of the same thing, because once you get this between minus pi and pi, it's really the same thing. Whether it be 2 pi or 3 pi, it's really a repetition of a similar thing. So what we're saying is that n can be n is a real number. So n being a real number, you're going between 0, well, between minus and positive value of n, which then makes this now, which you realize that this expression, all of this expression, based on what we have here, is going to go between either 1 or minus 1. And if that is the case, we can make this representation, because that now speaks better to representing this between plus and minus, because if it's minus 1 times 1 is going to give you 1. Minus 1 times 0 is going to give you any number raised to 0 is
1, sir.
okay. That is why we have a 1 right here. So that's why it's not necessarily any rocket science, Sir Verda. It's just a simple representation that we realize that from this here, this thing go between plus or minus 1. And the representation mathematically is that you could say minus 1, because this is going to give you, if you had this as 1, then it'd be an error in bracket. And why this be an error is because you will not necessarily get a minus quantity. Because remember, 1 to the 0 is 1. 1 to the 1 is 1 squared. So you'll never get a minus, so it won't give you a true representation of the negative value. That's why I have a minus here that is raised to the n. Are you clear?
Yes, sir, I got that.
Okay. All right, moving on. Or the video. Muting my mic again.
Right? So, I mean, I told you kind of what the forward Fourier transform is of a discrete time signal. How would I go back and get the discrete time signal from the Fourier transform? Well, let's again think about what does the continuous time inverse Fourier transform look like? Well, there was basically a integral from minus infinity to infinity, x of omega e to the j omega t d omega. Right? And actually there was a 1 over 2 pi out here, right? So what is the intuition for what the inverse should look like? Well, I would kind of hope that by analogy, I hope it kind of looks like the same kind of thing. 1 over 2 pi, except instead of integrating between minus infinity and infinity, I only integrate over one period of the dTFT, because otherwise I'd get infinity. So this would be my hope. And in fact, that's what turns out to be true, right? So I'll just prove why that's true, okay? So let me just consider the inside integral. So proof. Let's consider this integral, x of omega e to the j omega n d omega. Okay, so now I'm going to plug in my forward dTFT formula, right? So I'm going to say that's equal to this integral, x of omega, and then I defined x of omega equals this. I'm going to use m here instead of n because I've got an n here already, and so for the purposes of this expression, n is already some fixed number. So I need to use a different variable here as my dummy summation variable. Okay. And so now what I would like to be able to do is to switch the integral and the sum, okay? Now, this is not a class on real analysis, but suffice to say that you can't always just arbitrarily switch the orders of integrals and sums. And so one sufficient condition that I'm going to tell you is that sufficient condition to switch the order is that if I sum up all of the values of the absolute value of x, I get something that converges, right? And so this may actually bring back some memories from maybe Calculus 2 when he talked about series and convergence of series and stuff like that. I need to know, okay, so when I add up sums, when I have an infinite series, what do the terms have to satisfy for me to get an answer, right? So you probably spent 2 or 3 weeks on this when you took calculus way back when. Okay, so this is one sufficient condition for the sum to converge. And so in that case, I can say that this integral equals the sum of these integrals, minus pi e to the j omega n minus m d omega. Okay? And so now I can stop and say, okay, well, this guy here is kind of like an integral that we had to do before when we were deriving the Fourier series, right? We were kind of saying, well, if I'm integrating a exponential, which I could decompose this into, you know, this is like this integral, cosine omega n minus m plus j sine omega n minus m d omega, right? Let's think about the cosine. When n minus m equals 0, what I have is this integral from minus pi to pi of 1 d omega, which equals 2 pi. When n minus m is not equal to 0, what I have is the integral from minus pi to pi of a signal that basically between this region is wiggling, you know, like this, or wiggling, you know, an integer number of times inside this interval. And so the point is that inside these integrals where n is not equal to m, I always have as much above the line as I have below the line. So all these integrals turn into 0 when n is not equal to m. And so that means that this whole thing here basically turns into, you know, 0 most of the time. For almost all of the values in this sum, it's 0. The only time that it's not equal to 0 is when n equals m. In that case, the integral is equal to 2 pi, and I can turn this whole integral into, I can turn this whole thing here into 2 pi times the one place where n equals m. And that's exactly where I wanted to get to, because if I look at where I started, I was looking at this thing, and I wanted to show that this integral here equaled 2 pi times x of n. And so that's where I got to in the end. Okay? So just to kind of put it all together, the DTFT is kind of characterized by the forward and the inverse, right? So the DTFT, to get the forward one, I take x omega is this infinite sum. And to go backwards, I do this integral over one period of the DTFT. Okay. So, questions or comments?
All right. How are we doing so far?
This was okay, so I understood. He just substituted the discrete time back into the way how the continuous function, the continuous Fourier transform is done to prove that the final equation that we got to do discrete Fourier transform. Discrete time Fourier transform. Correct?
Yeah. What about others? Any questions so far? Yes, Chad? Okay. All right, let's move on.
So one thing I want to start doing is drawing connections between all the Fourier transforms that we've learned about so far, right? And so this here actually should look kind of familiar, right? Because this looks a lot like how I would compute the Fourier series of something, right? So suppose that I had a signal, a periodic signal, where the period was 2 pi, and let's just say it looks like a Fourier series expansion for a signal with period 2 pi, right? Because what is that Fourier series? It's AK, the sum, basically over some region, my x of t, e to the minus j, then I have my kind of 2 pi over t, which turns into 1, k omega, kt, right, dt, right? That's the way that I would compute the Fourier series expansion of some continuous time signal that had period 2 pi, right? And so I can see that actually this looks a lot like this, right? So I have the same kind of 1 over t, I have this integral, I have a continuous time signal here that's periodic, and then I have this e to the j, some integer, t dt. And so actually, that's exactly what is happening here. And so one way to think about the relationship between the dtft and the Fourier series is saying, okay, what if I were to take my, what if I were to take my signal? So here's my original discrete time signal, right? This has some dtft that is 2 pi periodic. And so I can kind of draw, again, I'm just going to kind of sketch it out here. Right? And the idea would be that if I take this 2 pi periodic signal and I go backwards and I compute the Fourier series of this, these AKs are basically what I get. Another way of thinking about this is that if I were to convert this into a impulse train, where the heights of these impulses were the same heights as the discrete dots, right? So this is like turning it into a weighted impulse train. But if I were to take the basically, if I was to take the inverse continuous time Fourier transform, what I would get would be, again, the same thing here, right? We proved that before. We were saying, usually when I take the Fourier transform of something, I insist that when I integrate it, I get a finite number, right? Here, if I was to do this integral, I would get infinity because I'm summing up an infinite number of copies of stuff. But we made an exception for periodic signals. And in those cases, we said that if I were to take the Fourier transform of this, what I would get would be a impulse train where the heights of the impulses were the Fourier series coefficients. Okay? And so, all this Fourier stuff is basically kind of tied up together, right? There's not kind of like saying this is one entity and this is another entity. They're really kind of all the same thing under the hood. It's just a different way of thinking about whether they represent signals with sticks or with delta functions in continuous time or discrete time. So that's kind of the idea. I mean, there is a little bit of a, there was a sign flip over here. Like if you compare this to this, there's a negative here and a positive here. But that's just kind of a convention as to which way I define forward and inverse. So it's not really a substantive difference. Okay. So comments or questions about this? And again, so I'm not going to talk about it right now. And actually what I decided to do, and I see it's the way I said it in the syllabus, is that I'm going to talk about the Z transform next. So next week we'll talk about Z and solving linear time systems with Z, and then I'll come up just before the exam and talk about the fourth missing piece. So so far what we've talked about is if I have, I kind of like to make this table where I have on this side, I have a continuous or discrete signal, and then I have either a periodic or a non-periodic signal, right? So we kind of already showed that when I have a continuous periodic signal, I take the Fourier series. When I have a continuous non-periodic signal, I take the Fourier transform. Okay? And so we just kind of showed here was, if I have a discrete non-periodic signal, I have the discrete time Fourier transform. And then we have yet to fill in this part of the square, which is basically going to be the discrete Fourier transform. So this is going to be, we're going to do this after we do the Z transform. But by the time we come up to the first exam, you guys are going to know about all four pieces of the square. Okay. So this is a little bit confusing, right? There's DTFT and DFT, right? It's poor notation, but at some point, I may, so after we get into the class a little bit more, I'm probably going to start just dropping the DT from this, and it'll be implied that if I'm talking about a discrete time signal, then of course we're doing the DTFT, right? So I may just start calling it the Fourier transform with the understanding that you know which one is continuous and which one is discrete. Okay, so I wanted to say a couple of little things about when the DTFT works. Okay, so we mentioned that if I have this convergence property, then we have what I would call, really good convergence. What that means is that the limit, so this is a little bit of a mathematical notation that not all you guys are going to know, but let me just put it down here for a second. So soup here is basically like the maximum value of the signal. What this means is that as n gets big, x of omega, or xn of omega, which is going to be like this partial sum where I only add up a finite amount of these things. In a way, that's like adding up only a finite amount of Fourier series terms. Is kind of one way to think about that. This converges at each point to the actual value. So it's kind of like saying that, if I tell you, okay, I want to have the true I want to have the approximation of my Fourier transform to be as close as possible to the true thing, I will get there if I add up enough terms at every point, right? There's a kind of a looser condition that says that if I have this instead, right? This is kind of a looser condition. What I mean by that is that there are signals that satisfy this that don't satisfy that. Then what I have instead is that the limit as n goes to infinity of this integral goes to 0. So kind of what this means instead is that it may not be true at every point exactly, but the difference, the integral of difference between the true thing and the approximation gets smaller and smaller. And so kind of one of the reasons for that is related to like the Gibbs phenomenon thing we talked about last time. So basically if I have, for example, the way that the Gibbs phenomenon approximates the square wave, right, there's always that little shoulder that's left, that 9% height difference that I can't really get rid of. And so that violates this condition, right? Because I'm always, for some point, going to be 9% away of what I actually want to be, right? But if I were to integrate the difference between the square wave and that Gibbs phenomenon approximation, the integral of that difference gets smaller and smaller and smaller. The shoulder gets narrower and narrower, so when I integrate that difference, it gets smaller and smaller. So this is what you would call mean square convergence, which is a little bit not as good as this. Okay, so what I want to do is a few examples, okay, to make all this a little bit more concrete. So far we're just kind of slinging formulas around. Okay, so let's start out with the pulse in the frequency domain. What does that correspond to in the time domain? So here I'm going to draw this pulse, which is kind of also like a low-pass filter, right? That's another name that we would give it. And so what would be the corresponding time domain signal? Well, I'm going to apply my formula. And I'm going to plug in, so this is going to basically be 1 between the two frequencies like this and 0 everywhere else. And this is not such a bad integral to do. What I get is 1 over 2 pi j n e to the j omega n over, or I guess I get like this, right? And so I plug this in and I get 1 over 2 pi j n e to the j omega cutoff n, e to the minus j omega cutoff n. And I can kind of immediately identify that, hey, you know, this is going to be a sine, right? This is like 1 over pi n times sine of omega cutoff n. And a different way of saying that is I have omega cutoff over pi times sinc of omega cutoff n. And so again, this is kind of like what we were expecting, right? A pulse in one domain corresponds to a sinc in the other domain. Okay? So we're going to talk about, and this actually illustrates kind of what I was talking about before, is that, you know, this signal, right, is, you know, this satisfies that the sum of the squared is less than infinity, but not that the sum of the absolute value is less than infinity. And so what I get, if I kind of consider these partial approximations in the time domain, if I kind of start from the middle and kind of add x of n terms, what I'll get in the frequency domain kind of looks like the Gibbs phenomenon over here. So what I'll get is something that looks like a approximate filter, and then I'll have, you know, something like this. And again, the fact that there's always this little guy here means that I don't converge at every point, but I do get something that's closer and closer. You know, eventually I'll get something that looks like, you know, this. So the integral difference between this and the square wave gets smaller and smaller. So I get convergence in that sense. Okay. So actually, maybe it would make more sense to go back and do some much more basic examples. So let's talk about you know, the standard things. So what happens if I have a delta function? So if I have a delta function in the time domain, well, in the frequency domain, I have this sum, e to the minus j omega n. The only time that this delta function fires is at n equals 0, so there's only one term in the sum, actually, and that corresponds to n equals 0 when e to the 0 is 1. So basically, I have this as equal to 1. And so, again, our old intuition is the same, where I have, you know, delta function in time domain corresponds to a constant value of 1 in the frequency domain. Well, what if I go the other way around? What if x of omega is the delta function, okay? just to be clear, though, we can't actually have a delta function sitting alone at 0 in the same way that we had for the continuous time Fourier transform, because everything in the discrete time frequency domain world has to be periodic. And so really, when I say that, what I mean is that I have a delta function that repeats every 2 pi units, right? That's something I can talk about because it's periodic. And so I can ask, what is the inverse Fourier transform of this repeating signal? Well, I would do this integral minus pi to pi of x omega e to the j omega n. Again, this delta function fires at omega equals 0 inside the interval of integration that I care about. And so that means I'm going to plug in n equals 0. This, again, I get 1, right? So I get 1 over 2 pi. And so the inverse Fourier transform of this is a constant for all n, just like I would want. And the height of that constant is, 1 over 2 pi. So it's still true that, a delta function in one domain corresponds to a constant in the other domain. I just have to be a little bit careful with what I mean by a delta function in this world, right? Because it's no longer just a delta function sitting by itself. So questions about this?
All right, so my question is to you guys, the same question. Any questions so far? So here somebody asks about, you guys had asked about working questions. Remember somebody had asked that earlier? Okay.
Yes, I remember someone else.
Okay. So are we seeing questions being worked now? I think it was Mr. Wright who had asked a question. And based on the question that was done, are you guys clear?
So on that last part, so that integral was done as the others with respect to dw, right? With respect to w, sorry. What did it say?
Yep, so with respect to omega.
With respect to omega, my bad. It's just that, so we know that if n in this case was 0, right? That then you would have basically the integral from minus pi to pi of e to the 0. You know that e to the 0 is 1, right? Yes, sir?
Go ahead, I'm listening. I'm listening.
Yeah, so in the event that n is equal to 0, and then you have e to the 0 being 1, when you work that integral with respect to w, and with respect to omega, you'd just get omega, right? And then you would sub the limits. So you'd have what? You'd be having pi minus pi, wouldn't that be pi plus pi, which is 2 pi, and then wouldn't the 2 pi cancel the other one in the denominator? And leave you with just 1?
So
Or is that too much?
what are we integrating with respect to?
Omega.
Okay.
Mm.
So omega is what?
The frequency, right?
Expressed as?
Expressed as, I don't know.
2 pi. Integral function with a function that is being integrated. You follow
Wait,
me?
what? Repeat that?
All right, so let me go back. Let's go back to the page. Go back to the representation. So what we have is, are you talking about this expression?
Yes, sir, that one.
Okay. So if you have this expression, you're going to integrate, right?
Mm-hmm.
Okay. this is a constant, which is already outside. Nothing else that is here is a constant. Because we're going to integrate this function with respect to omega, right? And omega, omega is a function of pi as well, right? Okay. So, from my little knowledge of math, how you go about the process, the integration process? What do you do first?
Well, you're looking at. Are you looking at this entire thing as one expression, or is the x of omega, and the e to the j omega n are two different expressions? Because I think them have a particular integration technique for if it's two different stuff.
Doesn't matter. It's called integration by parts, but it doesn't matter.
Yeah, integration by parts.
Yeah, so it doesn't matter. What I'm saying is, how do you go about, how do you approach it from an integration perspective? So whether by integration by parts or
substitution.
Yeah, how do you go about?
Well,
and this is for anybody, anybody.
Yeah, so using, where you going? Oh, you went back. You went further back, sir? Sure?
Yeah, man, I'm still here. Sorry about that.
You went further back on the video.
Oh, my apologies. That's in my hand. I don't want to pass where.
I think it's forward. I think it's towards the 31.
All right, so listen to this. Listen to this again.
All right.
Because it's periodic. And so I can ask, what is the inverse Fourier transform of this repeating signal? Well, I would do this integral minus pi to pi of x omega e to the j omega n. Again, this delta function fires at omega equals 0 inside the interval of integration that I care about. And so that means I'm going to plug in n equals 0. This, again, I get 1, right? So I get 1 over 2 pi. And so the inverse Fourier transform of this is a constant for all n, just like I would want. And the height of that constant is, 1 over 2 pi. So,
okay, so let's pause right there. What do you get from that?
That the function x of omega, after you perform your integral, you're still gonna get basically end up with 1 over 2 pi.
All right. What happened is that when n equals to when n equals to 0, right?
Yes, sir.
What's gonna happen to the function? The function, when n equals to 0, we're gonna have e to the j omega is gonna be, j omega is gonna be 1, right?
Yes, sir.
Okay. X omega is gonna be what? You're moving between pi, minus pi and pi. You remember what you did when you go like and both, right?
It's still true.
Oops, right. Doesn't matter. Right. So what it's saying is that between pi and pi, when you drew the function, the amplitude is 1, right?
Yes, sir.
Good. So we're saying between pi, because this is going to be raised to become 1.
Yeah.
Between pi and 2, between minus pi and pi, this value is actually going to be 1.
Mm-hmm.
That's what this is saying, eh?
Yes, sir.
Which is why the integral of 1, no, that's going to be a constant, so that's going to come out, right?
Yes, sir.
So that's why we end up with at n being what? 0?
Mm-hmm. Yes, sir. In this case,
right? The value. So we're looking at n being 0 initially. The value.
Also, the function.
Yeah.
Yeah.
Is going to be
for any case of n, it would be 1/2 pi.
Exactly.
So 0, 1, 2, 1, any number that n would come out in the function, it would be equal to 1/2 pi.
Yeah. So that's kind of how you reason it without actually have to start to give yourself headache about what I need to integrate and what needs to be done. Because really and truly, see, you're going to talk about integration by parts. I really don't want to get into that, right?
No, but that's why what do you call it there? That's why before, when I just started asking about it, I wasn't even asking about integration by parts. What I was noticing is that the e to the 0 would become 1, leaving you with the function x of omega, right? And you said in that case it would be 1 as well, right?
Yeah.
And between the limit of negative pi to pi, like going with after you integrate a constant, it becomes whatever you were integrating with respect to. So so that's what I know of. So in this case, if we're integrating with respect to omega, I was figuring the 1 would become omega, right? And then I was figuring that the limits negative pi to pi, you'd proceed with those substitutions and then work it. That's why I was confused, because I thought that you would end up after that integration with 2 pi, and then it would already be multiplied by the constant, which was 1/2 pi. That's why I was confused.
Oh, okay. So this is actually showing you this, that between minus pi and pi, the function goes up and it's going to stay at 1 between. That's what he drew before, right? It represented that between minus pi and pi, the function is 1.
So he just used the graph of that diagram to dictate that.
No. Remember, no. It's because of what n is. You're gonna start with n. So whatever n value of n that you put in. So if n is 0, this become 1. If n is 1, what happens?
If it's 1, you still have e to the j omega.
Exactly. And that is going to go between pi and
yeah. Still gonna give you 1? Give you 1/2 pi?
Yes.
I see.
I'm guessing because x omega is 1 at no matter what value of n.
Remember x omega is going to be the unit circle, really. You know?
Yeah.
You remember? Where on the unit circle is going to be? Is it going to be positive or negative?
Positive.
And that determination is dependent on what's happening here, the function itself. Remember, I showed you before when the whole function remember e to the j omega t can be represented as cos pi n plus j, right? So what happened is that that depends on know what the value of n is at different time intervals. Remember, we're talking about integers at the time intervals we're talking about for discrete signal, right? But so that's pretty much what's going to happen, because this is going to be the unit circle, all right?
Yes, sir.
Which is either going to be 1 or minus 1.
And it falling in within the unit circle provides the function of 1/2 pi.
Exactly.
Sir, I was saying that I realized that you.
Sorry, go ahead, Mr.
The fact that we were using back the equation from earlier, we derived the 2 pi times x of n is equal to the Fourier series. But the fact that we are dealing with the frequency domain, it seems like you put it in a format and made an assumption that between pi and pi, the fact that it's 0, and then proceeded to treat it as a discrete signal, though it's in the frequency domain. I'm not sure if I'm on the right path thinking that way, but yeah. Am I off, sir?
I'm not sure if I understand the question. All we're doing, right? All we're
Yes,
doing
sir.
right is that you take this expression x of n speaks to the going to the DTFT, right? Which is the discrete function. And that generally can be expressed in this form. Okay? The thing is, we know that the function of a Z transform or the discrete function lies on the unit circle. It is somewhere on the unit circle. It's a complex expression, remember? Complex number expression. It lies somewhere on the unit circle. Either on the right side or the left side, downside, upside, somewhere. What makes it, and again, you get a little bit more of that. I don't know if you did it in control systems. What makes a determination as to where on this circle? A couple of things. One include the poles on where the poles and the zero falls. And that sometimes is dependent upon the angle. Because sometimes you gotta think about the angular velocity to not only to include the frequency or to include pi, but it includes pi plus theta. Good? So without getting there to come to make it complicated, what we're saying is that somewhere along the unit circle, the function is gonna fall. So we know the magnitude generally is gonna be 1, but where it falls is depending on whether that is actually on the real or imaginary side, and depending on whether or not it's actually also is within the region of conversion. So this function x of n is generally and can be generally represented as this. What makes the difference, as I said before, it all depends on where it actually falls. Are you following me so far? So I'm not 100% sure of the question in terms of the assumption. Hold 1 second for me, guys. Hold on. Let me get back to something. Yeah, sorry about that, guys. I am back online. Yeah, let's continue. Let's see if we can see another example and see how we move from there. All right. Which one is it? This one.
That, you know, a delta function in one domain corresponds to a constant in the other domain. I just have to be a little bit careful with what I mean by a delta function in this world, right? Because it's no longer just a delta function sitting by itself. So questions about this? So another thing that we see all the time is exponentials, right? And so if we have an exponential that looks like this, and again, the reason that I'm saying it this way is that I want something that satisfies my rule about being able to sum up the values, right? So if I have an exponential that is decaying at 0 over here, I know that this is a valid signal to sum up, right? We already know what the infinite sum formula for this signal would look like. So that satisfies my rule. That should mean I could take a Fourier transform of it. And now if I plug in my formula, I'm going to actually need to use that rule. I guess I'll just kind of put it in here. So that means that my sum turns into 0 to infinity, a to the n, e to the minus j omega n. And this is written in a different way as a e to the minus j omega taken to the n power. And now I use my infinite sum formula to say that since each one of these terms has a magnitude of less than 1, right? That's my requirement to use this formula. I have this guy here, right? So this is a complex function, right? So again, one thing to remember is that even though I may have a real signal, I end up with complex Fourier transforms, right? But we can look at the magnitude and the phase of this complex function to get a sense of what the filter is doing, right? And so let's think about, you know, sometimes what we look at is that the magnitude response, which is defined as the absolute value or the magnitude of this complex function, and the phase response, this angle, right? These are kind of, you know, complementary ways of looking at what this filter is doing, right? So let's think about what that means. Well, let's just look at the magnitude response for a second, because that's really what defines the character of the filter. Is it low pass? Is it high pass? Whatever. So what I want to know is, what is the magnitude response? Well, it's the magnitude of this complex function. And again, a is going to be some real number, so I'm going to expand out this guy into 1 minus a cosine omega, that's the real part, plus j a, I guess I have a, yeah, sine omega, because this minus and this minus cancel each other out. And I'm going to, so that's this complex number. So my magnitude is going to be equal to 1 over the square root of the real part squared plus the imaginary part squared. And I can kind of think about what that looks like, right? So when omega is equal to 0, so when omega is equal to 0, I get this part is 0, this part is 1 minus a squared square root. So this height here is 1 over 1 minus a. And so since a is some number that's less than 1, this is some number that's greater than 1. And then as omega gets bigger, this number is going to get smaller, this number is going to get bigger. When I arrive at pi, what I'm going to have is 1 plus a over here squared, and I'm going to have a 0 again over here. So I'm kind of going to have a function that looks like this. that starts out high and dips down, not to 0, but to this value like this. And so this basically looks like, a crude low-pass filter, because stuff in the middle is getting passed through and stuff at the edges is getting attenuated. I'm going to say more about the magnitude and the phase responses in just a few minutes. Let me ask if there are any questions about how I kind of got to this point. So,
All right. Any questions on how we got that part?
No, sir. The only question I would ask is, I'm guessing the replica reflection of what's on the left-hand side. I know you get that from the equation by moving out to negative pi. It's a reflection, right? That's correct? To say it's a reflection.
It is a reflection around the axis, 0 axis.
Oh, okay.
Only because of the function, the type of function that it is. What happens is that at 0, I always remember something about cos and sine. All right. So at 0, we're gonna have, because at 0 we're gonna have the J sine omega section being 0. But the cos function, the cos part of it, because the cos function is going to be the highest at 0. Remember that? Because cos of 0 is? Cos of 0 is 1, right?
Yes, sir.
Right, so we're going to have the highest function of that complex number at that particular amplitude. And then it's going to decrease. And that's why I said that it's what do you call it? It's a decreasing in amplitude function. That means it's unlike the one that you saw before where the function was just 1. We see is that the function amplitude is reducing as pi is varying. And that's because of the function itself. So if you go back to here, I think we probably need to go to the other page first. All right, probably a little. All right. So right here, guys, I want you guys to look back at the video.
And again, the reason that I'm saying it this way is that I want something that satisfies my rule about being able to sum up the values, right? So if I have an exponential that is decaying at 0 over here, I know that this is a valid signal to sum up, right? We already know.
Not hearing, sir.
Sir, you're mute.
I'm sorry about that. You see, you're switching between. All right. So what I'm saying is that this is a function, and what I was told to you is that a function, the magnitude of a, which is a real number, is less than 1. Okay? So a is less than 1. But it was also told that here, anything below 0 that's negative is 0 value. So the function really is going to go from n equals to 0 up to pi. So it's going to go in this direction. And it really doesn't matter in this direction because it was stated that everything minus pi is going to be 0. Are we clear on that?
Yes, sir.
Okay.
Know what the infinite sum formula for the signal would look like. So that satisfies my rule. That should mean I can take a Fourier transform of it. And now if I plug in my formula, I'm going to actually need to use that rule. I guess I'll just kind of put it in here. So that means that my sum turns into 0 to infinity, a to the n, e to the minus j omega n.
Do we follow that part?
Yes, sir. It's just doing what the graph above said.
Exactly. So that's where we're going from 0 to infinity. But as far as this infinity is concerned, infinity is just going to be pi because it's a repetition. Remember I told you that, right? After a period, after pi, it's just going to be a constant repetition of the same thing. Start and go back, start and go back. All right?
Yes, sir.
So all we're doing is just, this is a function. But we're going to go from 0 and not minus infinity. Okay? So n is going to go from 0 upwards. Okay. So let's continue.
And this is written in a different way as a e to the minus j omega taken to the n power. And now I use my infinite sum formula to say that since each one of these terms has a
Mathematically, students, we would not have violate any form of a mathematical aspect. Because remember, we're talking about what? Integers, right?
Yes, sir. And at 0, it's 1.
Exactly. All right. So let's continue.
the magnitude of less than 1, right? That's my requirement to use this formula. I have this guy here, right? So this is a complex function, right? So again, one thing to remember is that even though I may have a real signal, I end up with complex Fourier transforms, right? But we can look at the magnitude and the phase of this complex function to get a sense of what the filter is doing, right? And so let's think about, sometimes what we look at is that the magnitude response, which is defined as the absolute value or the magnitude of this complex function, and the phase response, this angle, right? These are kind of, complementary ways of looking at what this filter is doing, right? So let's think about what that means. Well, let's just look at the magnitude response for a second, because that's really what defines the character of the filter. Is it low pass? Is it high pass? Whatever. So what I want to know is, what is the magnitude response? Well, it's the magnitude of this complex function. And again, a is going to be some real number, so I'm going to expand out this guy into 1 minus a cosine omega, that's the real part, plus j I guess I have a, yeah, sine omega. Because this minus and this minus cancel each other out. And I'm going to, so that's this complex number. So my magnitude is going to be equal to 1 over the square root of the real part squared plus the imaginary part squared. And I can kind of think about what that looks like, right? So when omega is equal to 0, so when omega is equal to 0, I get this part is 0, this part is 1 minus a squared square root. So this height here is 1 over 1 minus a.
All right. You see how we got that?
Yes, sir. Use the value of 1 for the value of hold on.
So it's like when omega is 0, the cos of the
zero, we're right here. When omega is 0, we're right here. Agree?
Agree, sir.
Okay. All right. So right here. When omega is 0, the sine of 0 is what?
0.
0. So that is out of the equation, right? So all we have left is this part at omega equal to 0. The cos of 0 is 1, right?
Mm-hmm.
So it's going to be 1 minus what?
The a times 1. A.
Right. 1 minus a. 1 minus a squared.
Square and a square root.
Right? So that's why we get this part. Clear?
All right.
That is at this. And that's why I was saying that starting at any omega equals 0 equal to 0, you're going to get the highest point because the cost function is the one that's going to be highest at that point. All right?
Amen, sir.
And so since a is some number that's less than 1, this is some number that's greater than 1. And then as omega gets bigger, this number is going to get smaller, this number is going to get bigger. When I arrive at pi, what I'm going to have is 1 plus a over here squared, and I'm going to have a 0 again over here. So I'm kind of going to have a function that looks like this, that starts out high and dips down, not to 0, but to this value like this. And so this basically looks like, you know, a crude low-pass filter, because stuff in the middle is getting passed through and stuff at the edges is getting attenuated. I'm going to say more about the magnitude and the phase responses in just a few minutes. Let me ask if there are any questions about how I kind of got to this point. So it's a good practice to be able to think about how to draw magnitude and phase responses by looking at the absolute values of these complex numbers, right? So let's talk about the, I talked about how a pulse in the frequency domain corresponded to a sink in the time domain, right? So what does a pulse in the time domain look like? So a pulse in the time domain. So let's suppose that to make things easier, I center this pulse. So I'm going to say it's just going to be between minus m and plus m for some integer m. And that's going to be 0 everywhere else. So my Fourier transform of this is going to be the sum of the values of the signal, e to the minus j omega n. Here I'm going to have only 2m plus 1 non-zero elements, each of which is going to be of height 1, let's say. And what I can do to make this a little bit easier is I can take out a e to the j omega capital M. That's like saying that I can instead start my sum at 0 and go up to 2m. Right? This is just a little bit of a mathematical trick, because this is like saying that, you know, when n equals 0, I get e to the j2 capital M. When n equals 2m, I get basically e to the j omega minus capital M. So basically I'm getting the same terms in the sum, I'm just kind of reordering them. Because now this is something that I know the answer to because it's a finite sum. So I can use my finite sum formula to get that this is like 1 minus e to the minus j omega to the 2m plus 1 over 1 minus e to the minus j omega. Right? This is a, you know, finite sum formula expression. So now let's think about this for a second. So actually, let's think about this here before I went to this formula. So when omega equals 0, this is just like adding up a bunch of these terms here, right? So that's like saying I'm adding up from minus m to m of a bunch of 1s, right? So my x omega here is going to be 2m plus 1. The reason that I mention this is because when omega equals 0 here, I kind of get a 0 over 0 and I'm not sure what to do with it. So I'm just kind of laying this aside. So let's suppose that omega is not equal to 0, and let's see if I can simplify this a little bit more. So this is going to be a little bit of a mathematical trick again. So what I'm going to do is I'm going to say, okay, I'm going to keep my e to the j omega m out here, and then in the bottom, I'm going to take out a e to the minus j omega over 2. And then what this turns into is this. And you can kind of see the reason I'm doing this is to make this look more like what I need to create a sign, right? So by taking out kind of halfway between these two things, I kind of get this sign. So this is like a professor's trick. In the same way, I'm going to take out half of what I saw up here, and I'm going to get another thing that looks like this. And now I'm going to say, okay, well, if I were to actually add up all these exponents, I would have an m plus a half between these guys, and here's my m plus a half over here. So all this stuff here cancels out to 1. And what I get is, here, this looks like basically sine of omega 2m plus 1 over 2. And this looks like sine omega over 2. And then I'm done, right? Because the two j's that I would normally have hanging around here cancel each other out. So I kind of got to a weird point here, right? Because, you know, here, this does not look like a sinc function, right? I kind of drilled into you all the time that a pulse converts to a sinc, right? But here I don't get something, I mean, I got something that kind of looked like it was going that way and then it didn't happen, right? Why didn't it happen? Well, remember that whatever I do in the discrete time Fourier transform world has to be periodic, right? And a sinc function is not periodic. So if I were to draw what this function looks like, it kind of looks like this. So between 2 pi and pi, this is going to be my poor artist rendition. I guess if I was smart, I could do this in MATLAB. So what it kind of looks like is something like this, where it's kind of the closest I can get to making a periodic version of the sinc function. It kind of looks like what I would get if I took sync functions, shifted them to be centered at multiples of 2 pi, and added all that stuff up, right? And in some sense, that's exactly what is happening, right? And so if I were to look for a closed form expression for that summation, that sine over sine that I have on the previous page is what I would get, right? So the intuition is still good. The intuition is still that a pulse converts to a sync, but the kind of sync that I get in the frequency domain has to necessarily be a little bit modified to make it periodic. So that's why the functional form is a little bit different. But if you were to look at the picture, it still kind of gives you that syncy feeling. Okay. So comments or questions on that? Okay. So let me say a few words about, again, why we care about these kinds of DTFTs of impulse responses, right? Because all we want to do in this course is analyze how systems operate on signals. And so usually the first signal that we're going to take the DTFT of is going to be the impulse response of whatever system that we're thinking about. And so let's remember that, we want to use the DTFT to study LTI, linear time invariant systems. So let's remember, well, so let's prove that, our convolution property still holds. So let me prove why that's true. So let's say that I have y of n is going to be x of n convolved with h of n, right? And again, this is convolution in the easy way, right? So if we're going to do like the Wozni convolution array method or the infinite sum method, right? This is the kind of convolution that we need to do in this class for discrete time signals. And so let's think about what is the
All right. Don't want to confuse the guys too much right now, but I'm gonna. Any question up to here? Because I'm gonna be looking at convolution a little bit differently. What I really wanted to show you before, or the was how it is that we to understand this the continuous time Fourier transform and the discrete time, the DTFT, and how do we transition between both, and the given functions, how it is that we can represent either one from the other or from the DFT to the CTFT. That was pretty most of what I wanted to get through to you in this presentation.
Sir?
Yes.
So you're saying what was just shown is how we convert between the DTFT and the CTFT, correct? How we go between both.
Yes.
Okay. Because at some point I was still trying to make the connections, because I realized that we use well, I know that it's still continuous time, but it's been in digital or discrete continuous. So sometimes I got, so it was good that you made to show us that we are that it's actually between converting from one form to the next, because I was a little bit confused, and I would think I was probably asking that earlier, but I probably asked it wrong.
All right, I'm gonna leave it there. We're gonna be touching a little on convolution the next time, but I hope that brings home the first part of the syllabus really. So we'll have completed the DFT, DTFT, and CTFT. Generally what those are, the expression, how do we go through them? We'll have look also at Z transform, region of conversion, and a couple of practice questions. I'll post some more up. I'm gonna post some more up of the conversion questions wise as well. And as I say, I'll get back to you, Chad, hopefully by tomorrow latest in regards to the way forward, all right?
Yes, sir.
Ooh.
Wait, you said by tomorrow?
Yeah, I'm expecting
A reply.
a reply by tomorrow so I can do.
Alright, cool. Remember to post this and the other lectures as well, sir.
Oh yeah. All right. There's no other question. That's where I'm gonna leave it tonight, students.
Alright, sir.
Sir, question. As it relates, you said you were going to give us some kind of Z transform assignment, sir?
Yeah, man, I'm gonna post the assignment.
Okay, sir.
Anything I'm gonna give you like that, it's gonna be posted. I mean, so you can always go. You don't have to ask somebody else. It's always there. You can go. I posted the due date, and I'll also provide you in terms of how to upload the answers. All right.
All right, sir. Much respect.
Okay. All right, guys. Take care. Have a good night, and we'll link up between with Chad, and we'll link up back by Tuesday, Wednesday. All right.
All right, sir.
Okay,
Cool,
sir.
sir.
So